there is a unique integer z such that x plus c is y. I changed the variables a little bit from the way I had them at the beginning, but of course it's the same thing, right? So how do you solve something of the form? Actually, let me change that. A plus x equals b. Well, this theorem answers the question for you. It says that every time you have two integers, a and b, if a, b are two integers, then there's a unique integer x that solves this equation, and we're done. Let's prove this. This is like the main theorem of the section. The proof is like really short. So let me think about this. So suppose, let's pick representatives for this. And we can do that because we know everything's compatible with the representatives. Suppose that this must be true because by definition these are integers. Sorry, I should probably add this class right here, right? And what, PQ again, PQ, right? Then take Z. The solution is just the difference, right? How do you solve this? If you already know about the integers, how would you solve this? Well, you just subtract, right? You just take a this. Sorry, that should be a b. Why did I write that like that? B. Right? You just subtract a from b, and that is x. So how do you make sense of b minus a? Well, b minus a should be what? P times n q times m. That's the way I defined it earlier, at least. That makes sense. Now that makes sense. Right? So now we have subtraction, because this x is literally the subtraction, right? It's literally the difference between b and a. So actually, why don't we go ahead and use that? So the notation is that x is denoted by b minus a, something that we already knew in the comments in green, but now the dreams have come true. This is the actual difference. And you can think about what properties subtraction has, right? Is it associative? Is it commutative? Of course, it's not going to be commutative, right? Let me just finish the diagram then, if we know this. So these are just the tuples, but flipped. Someone was saying in the chat. Right? That's the same thing. So how are we going to denote these? Well, we don't really know. These are the ones that we're introducing, so we're just going to add a minus in front to represent what they are, because they could be realized as 0 minus. And something that you may want to think about is, if we add a minus in front to represent negative numbers, why don't we add this symbol in front of numbers to represent fractions, right? Feels like something perfectly natural to do, and yet almost no one does it. Maybe we can do it here with the whatever, I don't know, stigma on that. Okay, so this finishes the construction of the integers. I didn't explicitly tell you what the ordering is, but you can using the theory that we have so far, it shouldn't be too difficult for you to fill in those details. There's a couple of exercises that I didn't prove, like filling in the details of the theorem. None of those is really that deep or that important. But now we did it, right? We extended the natural numbers to the integers. And the thing that we are now going to call natural numbers are going to be the copies of the natural numbers inside the integers, right? So from now on, so that everything is compatible, from now on, we will think of the naturals as inside the integers, right? Because of course we want to be able to work with both of them at the same time without having to do all this weird notation nonsense. So the natural will simply be the set of 0 in the integers, 1 in the integers, and so on, which of course you knew, but I don't want to have two different symbols every time I do this. We already know that the product and the sum and the order, everything is compatible. So what's the point of having like a subscript every time I do this, right? Because the sum and the product should have a subscript when you're doing naturals or integers. Let's just drop all that unnecessary notation and just take the integers as a whole, right? So the natural numbers are contained inside the integers in this sense. And this finishes the construction. And now we're going to do I'm going to define a new type of order for you.